All right, so we're moving away from acidic conditions into basic conditions. And so under acidic conditions, our nucleophile always attacks the most substituted carbon. Under basic conditions, you will not be surprised to learn it switches completely and we attack the less substituted position. And we'll talk about why that is in this video and also just going to do some examples under basic conditions so you can see what types of nucleophiles we might be talking about. All right, so under basic conditions, the nucleophile will attack the less substituted carbon. Substituted carbon of an epoxide. Okay. All right, so as an example, let's go back to our methylpropene here. We treat that with MCPBA, and we get our epoxide out. So last time we would then add H plus in our nucleophile. So we added H plus in methanol last time, and we ended up adding the methanol to the tertiary carbon, right? So we have two carbons to choose from here. We have a primary carbon out here. We have a tertiary carbon here. Let's use a basic nucleophile instead this time. So I'm going to use something like, let's use thiophenol, which is a sulfur compound. Sulfur is a very good nucleophile, and there's no H plus present. So under basic conditions, we're looking at things that are good nucleophiles, no H plus present, right? So basic conditions are generally going to be in the presence of nucleophiles, because nucleophiles are also bases. When this happens, this means that we are going to be, there is no positive charge or anything, and so we're really at the mercy of our nucleophile. The nucleophile is the thing that's going to start the reaction. And so we can think about the difference between acidic and basic conditions. Under acidic conditions, we always have these charged intermediates, right? We add H plus to something, we make the positively charged oxygen, etc. That's what controls the reactivity. So under acidic conditions, if we go back to our acidic conditions example, right? Under acidic conditions, we make this positively charged oxygen up here, right? And so with a positive charge, where is that positive charge going to be stabilized? Right? How do we make this positive charge in this intermediate more stable? And the answer is that we're going to put that positive charge at the most substituted carbon, right? It's like a carbocation. What makes it the most stable carbocation? When it has the most substitution. And so positive charge is stabilized best at the most substituted carbon. So when we have positive charge, we want to have that positive charge at the most stable or at the most substituted carbon, right? Just like a carbocation. Same thing with epoxides. If we have positive charge on our epoxides, we want that positive charge to be at the most stable position, which is the most substituted position, right? So, and then because the positive charge is at that most substituted position, that's where the nucleophile will attack, because the nucleophile is a weak nucleophile, like methanol, right, is just going to attack the place that's most positive. Now, under basic conditions, we have a good nucleophile. This nucleophile doesn't have to have a positive charge to react with. And so instead, this nucleophile with a good nucleophile will avoid steric hindrance. And avoid steric repulsion. And so that means that this nucleophile is going to attack the less substituted position. It's going to attack the primary position and kick open the epoxide. We'll lose the CO bond as a leaving group, and we'll end up with this here after we lose H plus, right? I'm going to throw that step in there for free. Right? Or I guess we could transfer H plus even. I'm going to do that. I'm going to transfer H plus from the sulfur to the oxygen, and we end up with an alcohol, but now the alcohol's on the tertiary carbon, whereas the sulfur, the nucleophile, ends up on the primary carbon. So compare that to what happened here, right? Our nucleophile, where's our nucleophile? Our nucleophile is here, attached to the tertiary carbon. The alcohol is here, attached to the primary carbon. Right, we've gone the other way this time. We have nucleophile at the primary carbon, alcohol at the tertiary carbon. So the selectivity switches. Under basic conditions, we attack the less substituted position. The nucleophile adds to the less substituted position. If your two positions are equally substituted, if you have two secondary carbons, then this doesn't help you, right? If there's no difference between the two positions, then they're going to be equally likely to react. And so you'll get nucleophiles adding to both positions. Right? So usually there will be a difference because we want to be able to have one product, one answer, right? But if there's not, then you have to know that you will get a mixture of things. Okay. I don't even know. Okay, so the last thing I want to talk about then is let's talk about a particular class of nucleophiles that we know are very good, and that is organometallics. Right? Specifically, we're going to talk about Grignard reagents just because those are the ones that we've talked about the most. But we know that these are, in general, very good nucleophiles. We use these as nucleophiles throughout the carbonyl chapters, right? And so when we use them with epoxides, so let's take, what should we use? Let's say that we make an epoxide that looks like this one. And I'm going to react that with a Grignard reagent. So I'm going to use cyclopentyl Grignard. Right, take a moment and think about what we know about Grignard reagents, what we know about acid, what we know about base, what we know about epoxides. Predict what you think the product will be. I'll wait here. Okay, you're back. So what's going to happen is that Grignard reagents are good nucleophiles, which means these are basic conditions. And so we go back to what we know about epoxides under basic conditions. We have to determine which of these epoxide carbons is the less substituted, right? So this one is attached to 3 carbons, that makes it tertiary. This one is attached to 2, that makes it secondary. 2 is less than 3, and so we know that our Grignard reagent will attack the secondary carbon and break that epoxide open that way. And so what we'll get out is we'll get this negatively charged oxygen over here with all the carbons attached to it, and we get something that's got a whole bunch of carbons. Right? But this is going to be our final product. So then we add H plus to that, and we get our alcohol. Right? That's going to be our product. Yeah. So that's what we get. We get Grignard reagents and organometallics in general are going to be always, every time, 100% of the time, no exceptions under basic conditions, right? So whenever you see an organometallic, you know that you're under basic conditions. And so we know that whenever we're opening epoxides under basic conditions, we're going to attack the less substituted carbon. So organometallics, always equal bases, always mean we attack the less substituted position.